All right, is this thing still on? Red dot, I think we're live. Hey guys, how's it going? Welcome back to the channel. I am back making videos. Took a little bit of a break, not gonna lie. The car's been being built, so I really just haven't had anything to film. Now, Smetic Performance is still rocking. We're still growing every single month, and I've just been super busy on the phones, taking care of customers, taking care of you guys, making sure that everyone's good to go. But I've got some updates on my personal engine that I wanted to show you guys. We're gonna do a little bit of assembly on it today and show you some new tech that's come out that I'm pretty excited about. Okay, so this is my personal 441 cubic inch LS7 race engine. It's got a Dart aluminum aftermarket block. It has our own Smeting crank and Smeting rods in it, and it has custom JE pistons. Previously on the dyno, this engine made 808 horsepower, and we did 75 hits on it to 8,000 RPM, with a couple of them going all the way up to 8,200. After that, we tore down the entire engine and inspected all of the components. So this is technically version 2. It does have new pistons. These are not the same pistons that ran that long. So these are 5 over, so it's a 4130 bore now. These are custom JE pistons, and these now have their new dual velocity gas port. So it has vertical gas ports, but they're on the very edge of the piston. You can kind of see some of them there. So that's a little new technology that JE wanted us to test, see how it does. It's supposed to have all the benefits of a vertical gas port, which can apply more pressure on the top ring than a lateral gas port, but by putting them on the edge of the piston, apparently they say the carbon buildup is almost zero, whereas on a standard vertical gas ported piston, eventually those are going to have some carbon and some soot building up in them. So, and we also increased the dome volume by 1 cc, so the new compression ratio will be 13.8 to 1 for this engine, which I'm running on pump E85. Again, it's a road race combination. It's not going to be 14.5 to 1 like a drag race engine would be. 13.8 should be spicy enough for what I'm trying to do. So with a little higher compression, with the dual velocity gas port, might pick up a little power there. We'll see on the dyno. Second, we tore the heads all the way down, inspected everything, and we noticed that the exhaust valves were all bent. Every single exhaust valve was slightly tweaked. Now, the only thing that can cause that is interference. So we inspected the pistons, and there are the smallest signs that the exhaust valves were just clipping the pistons as the piston was chasing the exhaust valve back into the cylinder head. So what can cause this? Two things. One, valve train instability. That's like 99%. And then 1%, the exhaust valve pocket and the piston not being big enough. It's not that, because I had over 100 thousandths of P to V, so it had to be valve train instability. So with these new pistons, I did go ahead and increase the exhaust pocket 10 thousandths, very minor, just to kind of check off the box and say I did it. The big thing though is previously we were running a stainless exhaust valve, now we have titanium exhaust valves from Victory. And these have the same hardened tips on them like the intakes valves do, so I can have full titanium valve train with no lash caps. So again, we're saving weight, there's less moving parts in the engine, more reliable combo. These exhaust valves are about 40% lighter than the stainless valves were. So by being so much lighter weight, should maintain stability and control over them better. Second, we are changing intake manifolds. I don't have it here yet. We'll show it to you in the next video, but the new intake manifold should increase our RPM range and get this baby up to maybe 82, 84, maybe 8,600 RPM. Because of the increase in RPM, I wanted to also step up the valve springs. Previously, the engine was running with a PSI 1513 valve spring. And with the cam profile that I have, which has 3/4 lift, it was, I think on the old combo was 0.753 or something, the seat pressure was around 140 and the open pressure was right around 500. We were running it really close to coil bind. I think it's gonna run out of valve spring control there. So we are now stepping up to a PAC 1237X spring, which will give me about 185 pounds on the seat and 585 pounds of open pressure. So whenever you increase valve spring pressure, well, for one, the valve spring pressure increase will help maintain better control as RPM potentially increases with the new intake. But whenever you do increase the valve spring pressure, it puts a lot more stress on the rocker arms. Now previously, version 1 of this engine was running a single 8mm bolt down rocker arm, no shaft mount, nothing special. Just one rocker arm per valve doing its thing. and it worked. It ran 8,200 RPM at 750 valve lift, was fine. Well, it wasn't quite fine, but it did it. Now we are stepping up to the real deals. We're going to run a set of Jessel Pro Series aluminum shaft mount rocker arms with complete one-piece tool steel mounts. And we opted to run a ball adjuster instead of a cup adjuster. So now the push rod, instead of having a ball on both ends, if it focuses, there we go. Now it's going to have a ball on the lifter end, but a cup on the rocker arm end. We'll get into that later, but it's way better and it will support more valve train in the future. Not necessary at the moment, but when in Rome, you might as well. So, Jessel rocker arm will take care of the stability issue. Cylinder heads have been machined to big 7/16 bolt holes. These stands are going to bolt onto the heads, and then the rocker arms will bolt to the stands. We're still staying hydraulic lifter. We're not going solid lifter yet. So we will set our preload with this adjuster nut on the back, preload that lifter, lock it down, and we're good to go. Now, speaking of new technology that's come out that we're getting invited to test, Comp Cams has a new lifter called the Evolution Hydraulic Lifter. Let me show you this. Looks like a normal set of lifters, same thing everyone's always seen. However, these lifters have a trick up their sleeve. I've already taken a clip out of this one, and when I tip it over, look at that little guy. Come here. That is the actual hydraulic component in this lifter. This is the hydraulic, I've been told, off the record, this is a very, very similar component that's found in a lot of dual overhead cam engines. Very small, has a very small oil reservoir, and can support much higher RPM than your standard lifter. And it comes out of the lifter body. I was told that the lifter body that these are made out of are the same ones Comp uses on their big dog solid roller stuff. Same body, same axle, same wheels, same bearings. So they're proven at crazy high spring pressure and crazy high RPM. And then they machined the inside to accept this hydraulic plunger. Now, they tell me that this plunger is a standard travel. It's not a short travel. It's a standard travel plunger, but because it has such a reduced oil volume in it, it has all the benefits of a short travel lifter without the headaches of it. So if you've never set up valve train on a short travel lifter with an LS engine, you have to nail the push rod length. And 9 times out of 10, you're getting a custom set because your tolerance is so tight. And then if you don't get it perfect, they're going to be a little bit noisy. Well, because this is supposed to have, or it does have, full standard travel, it's not as critical on the push rods as the true short travel lifters are. And guys, this is a serviceable item. Comp Cams will sell you this little plunger insert so that if they ever get noisy or any debris goes through them, or say you tear up a bearing and you send a bunch of trash through the engine and it clogs these up, all you got to do is pull all these out, and then for a couple $100 you can put new ones in and you've got a fresh lifter ready to go. I was told that they already have customers testing these around 600 pounds of open pressure at 9,000 RPM. And we're not quite there on the spring pressure, or we're actually not quite there on the RPM. We're pretty close to there on the spring pressure, so these should be perfect. So we're going to run these in place of the Johnsons for now, see how they do on the dyno, and give them a test. Everyone loves a little bit of testing. With all of that out of the way, guys, I'm going to start by assembling the cylinder heads with the full titanium valve train and the new pack valve springs. We'll get the install height set correctly for my cam profile. I'm going to run them with 50 thou of coil bind clearance. Testing has shown that if you run, it's better to run tighter to coil bind clearance than further away from coil bind clearance when you're pushing the envelope of what a valve train can handle. You know, again, high RPM, high lift, 750, and a little bit of spring pressure. So we'll set coil bind at 50 thou, we'll get the heads assembled, and then we'll bolt them on the engine block and get ourselves a push rod length. just like that, the cylinder heads are fully assembled. I was able to get the install height within 5 thou on each cylinder head, on each valve. PAC sells shims in 15, 20, 30, and 50 increments, so you can really dial it in on an application that needs to be incredibly precise. So I've already got the head gaskets on the block. Studs are all installed and lubricated with CMD high pressure torque lube. So we can now install the cylinder heads onto the short block, get them torqued down, and then we can start playing with the Jessel rocker system. Now that the cylinder heads are final torqued and installed onto the engine, we're now going to install the Jessel one-piece tool steel shaft rocker stands. One on each side, we'll torque them down, and then we can start getting our push rod length. And because the intake bolt hole for these stands goes into the intake runner, I'm going to run some PTFE thread sealant on the bolt itself to seal off that hole. That way we don't have excess oil consumption through the engine. All right, these shafts are installed on both sides of the heads. This set of Jessel rocker arms uses the same part number rocker for intakes and exhausts. Some of them use 2 different numbers. This set is all 1 number. So again, because that rocker arm has a ball adjuster on the very bottom, we're going to use a special push rod checker tool that has the ball end for the lifter side, but then a cup end for the rocker arm side. So I've already got the motor rotated over to 0, or to onto the base circle of the cam. And we're going to start finding just exactly how long this needs to be to get ourselves the push rod length. It's a little bit of patience, a little bit of trial and error, a little bit of back and forth until we get this guy on the money. I think that's actually really close. Okay, there we have a little bit of lash. So we need to make our push rod just a little bit longer, and then we'll be on the money. All right, so we got our length for the intake. I've already rotated the engine over to the base circle on the exhaust lobe, and it's probably going to be the exact same well, it's always good to check. Yeah, it feels identical. I'd say if you're doing this at home, it's probably not a bad idea to go ahead and final torque that rocker arm down. That way your measurement is as accurate as possible. I've done this a gazillion times, and I'm pretty confident in the feel that I have. Secondly, because we're using that Jessel rocker arm with an adjuster nut on the back end, we have adjustment, right? So I'm not trying to perfectly dead on nail the push rod length with this type of valve train, because I do have that ability to make small adjustments here or there. So we've got a push rod length. Time to order some push rods, and we'll pick up where we left off once they come in. While we're waiting for the push rods to come in for the engine, the intake manifold was just delivered. Dun, 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 dun. CID LS7 6500 throttle bore, and I ended up going with the 4.5 variant manifold per John at CID's recommendation for the plans with the engine. So these intake manifolds are pretty much the baddest out there, but they require a lot of attention to get them to work correctly and to optimize them for your engine. John makes these with much thicker pads on the flanges. That way they can accommodate a wider variety of engine and cylinder head designs. So right now, I don't know if y'all will see this. Let me get some extra light for you guys. So if you look in there, the intake manifold is sitting above the port of the cylinder head. Now, we can't remove material from the cylinder head to match the runner of the intake manifold. So what we're going to have to do is mill those pads on the intake to lower it into the engine. So we're going to cut material off the pads of the intake flange. That'll drop the manifold down, and we're going to mill them until the top edge of that runner just sits below the cylinder head. Then we can port match it and kind of remove a little bit of material off the roof. The floor has a ton of room to go, so we don't have any fear of lowering it too much, and then we'll be a little bit in trouble. So I'm going to cut those flanges down in the CNC machine. Let's figure out a way to fixture this so we can make that machining happen. And then once that's done, we can port match it. All right, this is what we're working with. We're in our Haas VF6, and we have a 4th axis rotary. So I have this big chunk of aluminum. I milled it perfectly parallel to the spindle. I then drilled and tapped it so I could put a couple long 1/2-inch studs in it. And then I machined a bar clamp that goes across the bottom of the manifold to tighten it down to this chunk on the 4th axis. Now with the rotary table, I can dial in and perfectly true and straight the manifold to our cutter so I can mill it parallel. So I'm going to dial indicate it, make sure I get everything nice and straight, and then we'll start cutting. Alrighty, first side is done. Let's check our surface finish. Ended up milling 165 thou. And look at that, looks like a mirror. So now we'll grab our 4th axis, roll this baby over, run a dial indicator off the other side, and we'll cut it to perfectly match the first side. Nice and straight and square and level in relation to our cutter. So I'm going to knock that out, and then we'll see you back on the engine to check our alignment. All right, we are out of the CNC machine. Again, we cut 165 thousandths off each flange. And now we can look down, if I can get the lighting right for you guys. It's hard to tell on camera with a flashlight, but there's no overhang on the roof of the port now on either side. So now what we can do is bolt the intake manifold down, torque it, and then we can come back and scribe the back of the flange following, the perimeter of the port, and then we can port the intake manifold to match the heads.
Push rods are here. So Smith Brothers, of course, and again we have the ball end on one side and then a cup on the other side for our Jessel rocker arms. So, time to put the push rods in the motor, and then we'll get these rocker arms installed, and we'll preload them, because again, we're still running the hydraulic roller lifter. We're not going to have lash, so we'll actually put preload in the lifter using the adjusters on the back of the Jessel kit. Okay, so with the lifters that we're running in the engine, they want to see 40 thousandths of preload. But since I have an aluminum block with the aluminum heads, I'm going to step that up to about 50 thou of preload just to offset for a little bit of thermal expansion. These Jessel rockers have a 3/8 adjusting stud on the back of them, and one full turn is 40 thousandths of preload. So I'm going to go 1 1/4 turn to get me that 50 thou spec. And so we'll just back this off until there's a bunch of lash. And then I'll run this down to take up any lash there is without collapsing the plunger and the lifter. Right about there. And then we'll go 1 full turn plus 1/4. And then lock it down. And these little adjuster nuts only torque to I think the spec is 22 foot-pounds. I'm just going to do it by hand. Something like that. Quick and easy. All right, that's one side down. Now we'll do the passenger side. That is the valve train done. We'll do a quick red net compression check. Make sure it's all there. Feels like about 14-1. So we are now going to also be testing the CID 4.5 6,500 flange throttle body, intake manifold on the new combo as well. Shay, our foreman, is getting it port matched to the heads at the moment and should be finished up here shortly. Something kind of like that. And even though this is going to have a 6500 series throttle body on top, we're still going to operate it with a drive-by-wire motor actuator. So the throttle body will be opened electronically based on the pedal, the factory C6 Corvette pedal. So that's really cool. We'll show you guys that system in the next video when this baby goes back on the dyno. So thank you all very much for sticking around. I apologize for not making a video in the last, it feels like 6 months now at this point. Life just gets busy. Smedding has been growing month and month and month, and but it feels good to get back behind the camera and start filming some more with some cool motors. So we'll see you guys in the next video where this monster will be on the dyno making some power.